made with ionic bonds. Okay, talk about bonds. And these ionic compounds are forming as a result of loss and gain of electrons. Elements, atoms give away electrons, become cations, and atoms collect or gain electrons and they become anions. So in the ionic compounds, we have cations and anions, and essentially the compounds stay together because the positively charged cations are attracted to the negatively charged anions. There is no other connection. It's an attraction of opposite electrical charges.
Like a magnet.
Then there is the other way, the other kind, which we have the covalent bonds or the covalent compounds, right? And when we have covalent compounds, we are essentially talking about covalent bonds, and in this case, we are essentially talking about sharing of electrons. Okay? Sharing of electrons. Sometimes we have equal sharing, and sometimes we have not equal sharing. Okay? If we have equal sharing, we have non-polar bonds, and if we have unequal sharing, we have polar covalent bonds, right? And this polarity is essentially controlled by the electronegativity of the elements. The electronegativity of the atoms that make the covalent bond. If the atoms that make the covalent bond have the same electronegativity, then the bond is non-polar. If they have different electronegativity, then it's a polar bond. And the larger the electronegativity difference is, the more polar the bond is.
And covalent bonds are between two non-metals, right? Non-metal.
Between two?
Two non-metals. Like, because I know ionic is two.
Okay, let's say between non-metals.
Okay.
But this is the point where everything that you learn in general chemistry becomes a little fuzzy, a lot of gray lines, okay? So, but generally, yes, covalent bonds we could have between non-metals, okay? What we are, in organic chemistry, we are mostly interested in the covalent bonds. We don't have that many ionic bonds in organic chemistry. We are going to see when we have ionic bonds, but most of the times we are going to be talking about covalent bonds. Now, the next thing, we said we have sharing of electrons, right? And the next thing that we worked on were the orbitals, right? When we go from the electronic configuration, we have the energy levels or the energy shells, right? Then we have the energy levels we go 1, 2, 3, 4, and so forth. And then we have the energy sub-levels, which are the SP, D, F, and so forth. I mean, in theory, they can go forever because there are no limits. And then we have from the sub-levels, we have the atomic orbitals. And it's important that we understand and we know the atomic orbitals because those are the ones we are going to use to make the chemical bonds, to see how we make the chemical bonds. And the atomic orbitals, we have the s orbital, which is a spherical orbital. We have the 3p which the three p orbitals are the px, py, pz, and all of them look like that. And then we have the 5d orbitals, and if we go further, we are going to have the 7f orbitals and so forth. But if we know the orbitals, because we are dealing with the octet rule, and we are dealing with valence electrons, the orbitals that are important for us are the s and the p orbitals, right? Because those are the ones, for each orbital, we said we can put 2 electrons. So if we have these 4 orbitals, the octet rule is fulfilled when these orbitals are fully occupied with electrons. Now, these are the atomic orbitals, and these, and with the particular situation of the carbon, we said, and I'm going to put the electronic configuration of the carbon. Carbon is 1s2, 2s2, 2p2, right? This is the carbon with 6 electrons, right? So these are the valence electrons of the carbon, right? And the valence electrons, and we see them that they are in 2 different energy levels. And we know that the carbon makes 4 bonds, right? In order for the carbon to fulfill the octet rule, it's going to make 4 bonds. And we went through the bonds yesterday, on Thursday, right? So in order to understand and explain how it makes 4 bonds, we have the hybrid atomic orbitals. Hybrid atomic orbitals. Where the hybrid atomic orbitals is a combination of the s and the p, and they look like that, right? One lobe is bigger than the other. Okay, I'm just going to put it. One lobe is bigger than the other. Now we are going to elaborate a little on those, but I want to finish what we started. So we can explain with the hybrid orbitals. Then we spoke about the structures of the compounds, and we said that the most common structure we have is the tetrahedron, right? With all equal angles, and from the tetrahedron, if we change one of the corners, we are going to make the trigonal pyramid. And for some molecules where we do not have fulfillment of the octet rules, we can also have the trigonal planar structure. These are the most common structures that we have or we are going to be seeing in our discussions. Now, what we are going to do today? We haven't finished what we said on Thursday. But we are going to do okay. Then after we went through all these things, we introduced a new way or a practical way of drawing molecules, right? And that is important. Skeletal structures. It's convenient, it's practical, it's easy, it's faster if we use the skeleton structures to draw the organic molecules. And basically the skeleton structures, we show the carbon-to-carbon bonds without the symbols, no symbols. We show the carbon to a heteroatom bond, right? We presume the missing bonds to be carbon and hydrogen, okay? So, I just remind you, if I draw this molecule over here, So we need to be able, when we see a skeletal structure, to interpret the skeleton structure, right? And that skeletal structure has 6 carbons, right? Every corner is a carbon. Remember, show the carbon-carbon bonds, but know the carbon symbols. And since every corner has 2 bonds, there are 2 bonds missing. That means the 2 missing bonds are going to be carbon and hydrogen. So the molecular formula for this is going to be carbon 6, hydrogen 12. I can change one of the corners to an oxygen, right? And in this case now I have carbon 5. Because I have 1, 2, 3, 4, 5, 6 positions oxygen, hydrogen 10, oxygen. That's the molecular formula. And if I have an end, if I have this molecule, right, how many carbons I have? 1, 2, 3, 4, 5. This is a carbon 5 molecule, and I have hydrogen 12. Okay? The end, the reason I put it here, the end is essentially a CH3 group. Okay? So this is what today. This is what we are going to be using from now on. The earlier we start using it, the better, the faster we become familiar with it, and the faster we are going to be able to do it. And the other ways of drawing it, the condensed structure and so forth. But this is the most convenient, the most practical one to do. Okay? So, what we are going to do today, after those, we are going to see, we are going to use, first we are going to say a few more things of how the chemical bonds, the covalent chemical bonds are forming using the atomic orbital structures. Then we are going to talk about functional groups, and then we are going to talk about the physical properties of the molecules. Okay, these 4 things. Physical properties, meaning melting points, boiling points, solubility in water. Functional groups, what kind of other groups we have in molecules, and then we are going to start by explaining the formation of the chemical bonds. Remember, when you started learning chemistry, the first thing that you learned was how the atoms are structured, right? And you were told, okay, we have a hydrogen atom. The hydrogen atom basically has 1 proton in its nucleus, and we usually put a positive charge on it, or sometimes you're going to write it like that. And around that proton, we have an electron. And most of the times they are going to draw it like that, right? Put that and the electron here, right? That's how most people, or the first interaction in chemistry. Then we can put more electrons and more electrons. In reality, this is not what happens. What we have a positive charge, and then we have the electron moving everywhere. Not on a particular orbit. It can move it moves all the time, and the only real thing that exists here is the attraction between the electron and the proton, right? So the proton attracts the electron, and because of all that motion, that's the reason that the electron stays close to the proton. And that's what we call an atom. But in reality, what we do, we think about the space that the electron is moving. Keep in mind, the electron is moving very, very fast. So if we take a picture, which is not going to be very time sensitive, what we are going to see, the electron moving kind in this space all around, right? So when we make a chemical bond, let's say you have two hydrogen atoms, right? 2 hydrogen atoms with their electrons coming close together, okay? And the other electrons over here. If they are at a distance, that the distance that we are going to call a chemical bond. And this is the other thing. We talk about the electrons as being pairs. The electrons, when they become pairs, they don't go next to each other and they hold hands and they go around like on a date or something, right? What we mean they are in pairs, they have the same energy. That's what we mean when the electrons are in pairs. So when I have the two protons or the two hydrogens together, the electron of this molecule, of this atom, is going to be interacting with that proton, and the electron of this is going to be interacting with that. But also they are going to be interacting with the other proton, right? So we are going to have two electrons in between, interacting with these two protons. And this is what we call a chemical bond. These electrons, if they have the same energy, they are going to be interacting. They are going to be attracted at the same time by these two protons. And because of these attractive forces, they are going to stay together. They are going to be working around. They are going to be flying, moving around these two protons. And they are going to hold these protons in this distance, which we are going to call a chemical bond distance. Right? These are the physics of the whole system. It's a system of two positive particles being attracted at the same time by two negative particles flying around. Now, if we are going to show that in terms of orbitals, we are going to have the s orbital of one electron, right? This is the proton, and this is the electron with the s orbital. This is the s orbital of the other atom, right? This is the s orbital of the other atom. They come together, okay? And we need to understand how these things happen. The two hydrogen atoms, they fly in space together. So how are they going to come close together? So the electron of one is going to be attracted by the proton of the other. When they fly in space together, at very high speeds, they are going to crash into each other, okay? And when they crash into each other, they are going to have a general area where we call it that the atomic orbitals overlap. In this area, right, both nuclei have power. Both nuclei exercise attractive forces. So when they reach that distance, we are going to have the electrons being attracted by both nuclei, right? It doesn't matter where they are going to be attracted. So now we have this common space, and this is the space that we call a chemical, forming a chemical bond. And the same thing is going to happen. I mean, if we are going to have the overlap of the s orbitals, we are going to have an overlap with the p orbitals, and we are going to have an overlap with the hybrid orbitals. I'm just going to put them over here so you get an idea. The hybrid orbital looks like that. I have the s orbital coming here and having the common space. The p orbital is like that. I have the s orbital coming here, and we have the common space of creating the space that we're going to have the chemical bond. And we can do the same thing. The p orbitals can overlap with themselves, right, to make this bond over here, or they can overlap with, or the hybrid orbitals can overlap with themselves. Let me make it here. So. Okay, and I don't want to make it to take you further than here, the whole idea is that we understand that the orbitals can explain the common space that the two nuclei can exert their attractions and hold the electrons in attractive interactions with them, so we can have chemical bonds. And now from this common space, you understand that if we don't have the same electronegativity, then we are going to have one of the nuclei holding the electrons more than the other. So let me show you how this one is going to happen. We go back to the hydrogen molecule. Go back to the hydrogen molecule, and we see here again. I'm drawing it over there. This is the hydrogen molecule, ds orbital. This is ds orbital of the other hydrogen molecule, right? Then the two of them come together to have the overlap, right? And now, when we fuse these two atomic orbitals, we are going to generate what we call a molecular orbital. And the molecular orbital is the space where the two electrons are moving in the particular energy, so they can interact with the with the two nuclei that we have. Okay? So this one now, the combination of the two atomic orbitals is a molecular orbital. So all these combinations that we have up here, they result in molecular orbitals the same way that we have them over there. So if I'm going to make the p orbitals, right? If I'm going to make the p orbital combination that I have over here, right? The molecular orbital from this one is going to look something like that. Okay, again, the orbitals are the space where the electrons that participate in that bond are moving. So if we have the same molecule, the same atom, the same nucleus, if we have a homoatomic molecule, right? Homoatomic molecule. Homoatomic bond, like a hydrogen, right? If we have a homoatomic bond like a hydrogen, this orbital is going to be totally symmetric, right? It's going to be totally symmetric. And we are going to have this nice round orbital. But if we have a heteroatomic bond, heteroatomic bond, hydrogen and fluorine, for example, right? In a hydrogen and fluorine situation, and we have the electrons, we have the hydrogen here, the fluorine here, and we have the two electrons moving. And here is the question. To which of the two nuclei are the electrons going to be attracted, these two electrons going to be attracted more? To the hydrogen or to the fluorine?
Fluorine.
Why?
Maybe electrical utility.
Strong.
Stronger how?
The electric negativity?
It's more electronegative. Why? Everything goes to the property that doesn't change. Fluorine is stronger, more electronegative than the hydrogen because it has more protons in its nucleus. The hydrogen has one proton. Fluorine has how many? 9 protons. So if you were an electron and you had a choice to spend time to be attracted by 1 proton or 9 protons, where would you be most of the time? Close here, right? So they are going to be attracted more than here. And because of that, the shape of the orbital changes. We are going to have an orbital now that in reality, most of the time the electrons are going to be spending it around the fluorine. So this one is a non-polar distribution of electrons. And here we have a polar distribution of electrons. Because the 2 electrons of the bond are going to be spending more time around the fluorine than around the hydrogen, right? So if they are going to be spending more time on this side and less time on that side, what are we going to have here? We are going to have excess of electrons. And over here, we are going to have deficiency of electrons. And every time now that we have to demonstrate the excess and the deficiency of electrons, we need to make these nice drawings, right? Mm-hmm. No, we don't.
Oh.
What we do, we go here, I write the bond, and I can put a little minus over here and a little plus over here, depending which book you are using, or it's going to be delta minus and delta plus, right? The plus and the minus show that we have, wherever we have a plus, we have deficiency of electrons, wherever we have a minus, we have excess of electrons. It means that the whole electronic charge over there is more than the protons, or the whole electronic charge is less than the protons where we have deficiency. Okay? And now that, by knowing that deficiency of electrons, again, this happens when you have heteroatomic bonds. We also have this separation of charges is called polarity. Okay? The word polarity itself means separation. So polarized societies, they are societies that are divided, that are separated. So polarity in a chemical bond means we have separation of charges. And the polarity goes, the positive is always at the less electronegative, and the excess always at the more electronegative element. So, and that one is also shown by a little vector that we can draw, pointing from the deficient to the excess side of the molecule, and this is the dipole, the momentum, the dipole momentum, or however we want to call it, right? So polarity vector over there pointing from the less to the more electronegative part of the more electronegative element in the chemical bond. So if we are going to determine how the polarity of a chemical bond, we need to first know the elements that they make the chemical bond. If the chemical bond is homoatomic, that means if it's made of hydrogen, if it's made of chlorine, if it's made of nitrogen, all these are homoatomic chemical bonds, covalent bonds, they are not polar. But if it's made of heteroatomic, if the bond is heteroatomic, is made of 2 different elements, hydrogen and fluorine, hydrogen and oxygen, hydrogen and nitrogen, hydrogen and chlorine, hydrogen and sulfur, carbon and oxygen, carbon and chlorine, boron and chlorine, all these different heteroatomic bonds where there is a substantial difference in electronegativity between the elements, then we are talking there is a sharing of the electrons to make the covalent bond, but the sharing is not equal. We have polarity, and the polarity of the bonds always is directed from the less to the more electronegative element. Okay, in the specific case of the carbon and hydrogen, carbon and hydrogen have, it's a heteroatomic bond, but for the organic molecules, we do not consider that bond as polar for two reasons. The electronegativity difference between the carbon and the hydrogen is very small. That's one reason, small difference in electronegativity. And the other reason is because all the organic molecules, or most of the organic molecules, have carbon and hydrogen bonds, so they are the matrix that the molecules exist. So we don't consider them in the we don't consider them as polar when we have them. Okay, now since we introduced that, before we go any further, since we understand how the chemical bonds are forming and how we have sharing of electrons to make the polar covalent and the non-polar covalent, we are going to say a few more things about them when we talk about the chemical about the properties of the organic molecules. But before we go there, I want to get you, I want to introduce you to the main groups, to the main organic, the main groups of the organic molecules, and basically the main families of the organic molecules. As we said, the organic molecules are made of carbon, right? And most of them are made of carbon and hydrogen. While I'm talking, just pass this around so you get a feeling of actual molecules, right? These are models, molecular models. This is what we call them. So everything that we said so far, you can play with them. So, functional groups. When we spoke about skeleton structures, we said that when we draw the skeleton structures, we draw the carbon-carbon bonds without the symbol of carbon. We draw the bonds to the heteroatoms with the symbols of the heteroatoms, and all the other bonds that are missing are carbon and hydrogen bonds, right? They are presumed to be carbon and hydrogen bonds because every carbon has to have 4 bonds.
I'm sorry, what does the color mean?
Oxygen.
Oxygen, oh. And for the blue one?
Is this nitrogen?
Blue is nitrogen, yes.
Okay, cool. Thank you.
Yes.
Is there a way that we can determine the difference in the electromagnetic field? Because, I mean, you said there's not much difference between the two. How do we
I didn't say anything about electromagnetic field, but
yeah,
electronegativity.
Negative, yeah.
Electronegativity, depending on the periodic table you are using, one of the properties of the elements that are on the periodic tables is a number, which is the electronegativity number. It goes from 0 to 4. The electronegativity number 4 is fluorine. Okay, with all the other elements, depending on their position towards fluorine, get a number lower than 4. The closer they are to fluorine, the higher their electronegativity.
So what is the difference to determine whether or not
It's a subtraction, right?
Yes, you subtract. If I have the electronegativity, if I remember correctly, the electronegativity of the hydrogen is about 2 point something, and the fluorine is 4. So the polarity between the fluorine and the hydrogen is 4 minus 2.1. Okay?
Every time I think I get it,
Okay, people.
something else. And I'm
When you go, the red balls are oxygen, the blue balls are nitrogen, the white are hydrogen, the black are carbon. And when I bring other colors, I'll tell you. Sulfur is usually yellow, chlorine is usually green. I think iodine is purple, depends on the model kit you are using. Going to the functional groups now. The functional groups are the characteristic groups of the families of the organic molecule. In other words, the interesting thing and the exciting or the challenging, whichever adjective you want to use, is that you can have one common functional group in a large number of organic molecules, which that common functional group can give them similar chemical and physical properties. Okay, and we have basically three main categories. One is the category where we have only carbon and hydrogen elements in the organic molecules. The second category is the one in which we have heteroatoms but only single bonds to heteroatoms. And the third category, we have heteroatoms but with multiple bonds, double and triple bonds. So we are going to start with the easy ones. The first functional groups, we only molecules which have carbon and hydrogen, right? The molecules that have carbon and hydrogen, we call them hydrocarbons. And you can guess already that if they are made of carbon and hydrogen, they are not really polar molecules, right? Carbon and hydrogen, no polarity. The only difference is that we can have molecules which have single bonds only, and those we call alkanes. Molecules which have at least one double bond, at least one double bond, we call alkenes, and I'm going to give you examples, don't worry. And molecules that have at least one triple bond, we call alkynes. And there is a last group, a special group, that we call, if they have this structure. If they have this structure, the hexagon with the three alternating double bonds, these molecules are called aromatic molecules. Okay? Examples, alkanes. This is an alkane. The simpler molecule, the simpler organic molecule that we have is this molecule, CH4 is an alkane, right? A molecule with two carbons, also an alkane. Now I'm going to switch to this one has 5 carbons, carbon 5, carbon 12, also an alkane. And the interesting thing about the organic molecules is that we don't necessarily have only open chain molecules, right? These are open chain molecules. You can see one carbon after the other, right? We can have branched molecules. We can have branched molecules like this one. Okay, so this one has 1, 2, 3, 4, 5, 6, 7, 8 carbons, carbon 8, hydrogen 18, right? Or we can have even cyclic molecules. These are open chain molecules, and we can have cyclic molecules, like that. Or a smaller molecule, or a little bigger molecule, or an even bigger molecule. Okay? So we can have many many combinations. The common thing is for all these molecules that I drew on the board, all of them are made of carbon and hydrogen, and they have, all the carbons have single bonds, right? Single bond, single bond, single bond, single bond. And that makes them, what kind of hybridization we have when the carbon has 4 bonds and all of them are single? Somebody said it. sp3 hybridization. Okay? 4 single bonds. sp3 hybridization. Okay? So these are the alkanes. For the alkenes, we have at least 1 carbon-carbon double bond. Okay? So, can I have a carbon-carbon double bond with 1 carbon? Think, people, I want to hear your brains squeezing out. Grinding. Can we have a carbon-carbon double bond with only 1 carbon?
No.
So be brave enough and say no. We need at least 2 carbons to have a carbon-carbon double bond, right? So this is the first member of this family. Two carbons to have a carbon-carbon double bond. And what is the hybridization of these carbons? If we have a double bond, what's the hybridization? sp2. The carbon on the double bond has an sp2 hybridization. Okay? And then I can make a cyclic of this one, right? Or this. I don't necessarily have to have only 1 double bond. I can have more than 1 double bond. Okay? Then I can have 3 bonds, 4 bonds, 5 bonds. We are going to see some vitamin molecules that they have 10 double bonds in the molecule, 10 carbon-carbon double bonds. But these are the structures of the alkenes. We can have the open chain ones, like this, with 1 or more than 1 double bonds, and we can have the cyclic ones with with 1 double bond or with more than 1 double bond. For example, if I take this molecule, I can make 2 double bonds or 3 double bonds in it, right? Just the same things that I said about the alkenes, I can say about the alkynes. The same question. We need 2 carbons to have a triple bond, and alkynes are the molecules which have at least 1 triple bond. These one, the molecules with the triple bonds, are the least common in nature. Most of the molecules that we find in nature, they have carbon-carbon single bonds and carbon-carbon double bonds. Carbon-carbon triple bonds, we don't find that many molecules. Lately, 1 molecule with triple bonds was found, which has about 14 triple bonds, one after the other, connected. But the same thing that we can have a triple bond, carbon-carbon triple bond, where I can have other carbons attached. I can have a triple bond in a cyclic system, but I'm going to have a large cyclic system to accommodate it. I can have more than 1 triple bond in a molecule. Okay, so that we have molecules with double, single, and triple bonds, and of course, I know you know the answer. The hybridization of the carbons here is a sp hybridization. The angle is 180 degrees because that part is linear. This one is 120 degrees because it's trigonal planar. And the angles over there are 109.5 because they are tetrahedrons, right? So since I ran out of space for this one, we are going to do the aromatics on the other.
I said the triple one. Oh, there's 180 usually.
Yes, it's always 180.
Always.
The sp hybridization means that you have 180 bond angle, 180 degrees bond angle. Okay? So, aromatic molecules. Aromatic molecules are molecules that have the aromatic ring. That ring over here is called the aromatic ring, and I'm sure you know which ring it is. That is the benzene. Okay, that's a very nasty, very useful material that we have been using for years, for decades, but also is very poisonous, and people who are exposed to it, they get bone marrow disease. This is benzene. It's aromatic, carbon 6, hydrogen 6, right? And all the angles over here are 120 degrees. All the carbons, this is all of them are sp2 hybridized, and this one is a planar molecule. Benzene is a planar molecule, it's a flat molecule. Where is it? I have it. Somebody has the model, so you can see it. I think I have it. Okay. So if we attach on this ring, if we attach other parts, you're going to have it has the open chain, it has the aromatic, it's still an aromatic molecule. We can attach other things on the benzene ring like oxygen, CH3, okay, that's still an aromatic. If I replace one of the carbons with the nitrogen, that's still an aromatic molecule. So we can have more than one kind. We can have many variations. The important thing is that being aromatic, usually it means that it's everything on the ring is sp2 hybridized, the angles are 120 degrees, and the molecules are planar. Now, and these are the hydrocarbons. All these four families that we spoke are the hydrocarbons. Now we are going to talk about the families with heteroatoms. Single bond heteroatoms with single bond. Carbon connected to a heteroatom with a single bond, right? So, the easier way to do it, the general formula that we are using for the hydrocarbons is RH. R being the organic molecule, H being the hydrogen, right? If I replace the H with X, right? What does X stand for? In general chemistry, X symbolizes the halogens. So we have the halides. Okay, X is fluorine, chlorine, bromine, or iodine. So if I take, for example, the molecule that I have, methane, right? I replace one of the hydrogens with a chlorine, I make the chloromethane. If I replace another hydrogen, I make the dichloro. If I replace another, I make the trichloro. And if I replace all of them, I make the tetrachloro. In other words, we can have one halide or more than one halide attached on the carbon. Another example, something that fluorides, right? If I put fluorides on the carbon and chlorides, right? If I make this type of molecules, You may not know it, but we are using them in our cooling systems a lot. We are using them as anesthetics a lot. Not these molecules, but molecules with similar chemical bonds. We are using them in our cooking ware a lot. All these things that are non-sticking cooking ware, all these are made of fluorine or fluorocarbon coating. But I mean, we don't have to use those. You can have, for example, if I take the chloro, I can make chlorohexane, I can make bromo, right? So anytime I can replace a hydrogen, I can make one of those. And I don't necessarily have to have only single bonds. I can have alkenes with halogens. We are going to learn many of these things as we move along. Another group, the next one that we are going to use after the halogens is with oxygen. Okay? If we replace the hydrogen over there with an oxygen. Okay? So if I replace the hydrogen with an oxygen, molecules which have, this is the hydroxyl group, right? This is the hydroxyl group, the OH. It's the same thing like you have water, right? If I put OH, the water is made of a hydroxyl group and a hydrogen, right? So these molecules that have the hydroxyl group in their structure, they are called alcohols. Okay? And we have just a couple of examples of alcohols. This one with one carbon, the one with two carbons, the one with three carbons. Or the one that we buy at the supermarket with a carbon inside. Okay? All these are what we call alcohols, and these are the small molecule alcohols. We can have a large molecule alcohols. For example, like I have the cyclic molecule over there, I can have the hydroxyl attached on a ring, or I can have a molecule with 2, 4, 6, 8, 10 carbons. I have a molecule with 10 10 carbons and one hydroxyl group, and not necessarily, I do not necessarily have to have only one hydroxyl group or in a molecule. I can have more than one hydroxyl groups. For example, I can have this alcohol with two hydroxyl groups, or I can have this alcohol, like over here, this alcohol with two hydroxyl groups, or this alcohol with three hydroxyl groups. Anybody knows the alcohol, the name of the alcohol with the three hydroxyl groups? It's called glycerol. I'm sure you heard it before. Okay? So these are molecules. We are going to see many of them. You don't have to memorize them now. I want you to be able to recognize them, not memorizing them. When you see a hydroxyl group, to know that this molecule is an alcohol. When you see a halogen, to know that this molecule is a halide, right? The next group, or the next family that we have, still with oxygens, okay? We're going to go another family with oxygens, and then we go to the family with nitrogens. So we have the carbon to oxygen, that's the alcohols. And if I attach on the oxygen another carbon, if I take the hydrogen over there, hydrogen group away, then we are making the ethers. Okay, and when we write the ethers, the general formula for the ethers is ROR prime. The ethers don't necessarily have to have the same groups attached. So just a couple of quick examples. This ether, where we have these two groups attached, or I can have this ether, right? Or this is the diethyl ether, one of the most common things that we are using. We can have, these are the straight chain ethers. We can have cyclic ethers, like this one. Or we can have this one, or we can have aromatic ethers. Or this aromatic ether. Important thing is that the oxygen is connected to two carbons. So if the oxygen is connected to two carbons, we have an ether. If the oxygen is connected through a single bond to one carbon, then we have an alcohol, and the other part of the oxygen has a hydrogen. So now we are going to look at with the carbon nitrogen single bonds. The same way, if we that we had before, if we have a carbon nitrogen single bond with nothing else attached on the carbon other than hydrogens, those we call amines. Okay, and just think of everything that we put up, replace the oxygen with a nitrogen. For example, if I have, the only difference is that the nitrogen makes 3 bonds, the oxygen makes 2 bonds. So this is an amine. If I replace one of the hydrogens with another, this is an amine, and this is an amine. We are going to learn the differences as we are going to be talking about. Important thing, oxygen, nitrogen, sp3 hybridized, trigonal pyramid, trigonal pyramid, low pairs of electrons everywhere. And we can have also, if the nitrogen has only 2 bonds, the other bond is a hydrogen, and we need to put it over there. Or I can have this model. Okay, so all these are amines, and we can have many of them, as many combinations as we have. And we don't necessarily have to have only one nitrogen. We can have more than one nitrogens, right? Like this amine. Okay, we can have more than one nitrogen groups attached on the carbon chain. No, nothing against it. Before we are going to go on to the carbon with double bonds, triple bonds now. Before we go on, another one that we don't see very often and we don't discuss very often are when we have carbon connected to sulfur. Okay? And carbon connected to sulfur is kind of interesting molecules because we find them in nature, right? You know which is the greatest source of sulfur from what we eat that smells very bad?
What is
Garlic. The reason that garlic smells very bad is because it contains sulfur. The eggs, when they go bad, smell very bad, right? The sewers in New York City or every big cities or every small city, they smell really bad. It's because of all these sulfur compounds that they have this not pleasant smell. Okay, when we replace the hydrogen with SH, we have what we call thiols. Okay, the counterparts of alcohols but instead of having oxygen, they have sulfur, right? They are the thiols. I'm just going to give you one example, the one that we had before, this one, or I always like to give the cyclic ones, because the cyclic ones are easier to draw, right? I don't have to leave open things. And if I replace that hydrogen with another, make it like that, these are called thioethers or sulfides. Okay, example, I put another group over there, or I'm going to go to make the cyclic one, or I'm going to give you the okay, so we saw functional groups with carbon and hydrogen, functional groups with single bonds, oxygen, alcohols, ethers, single bond, carbon and nitrogen, amines, single bond with sulfur, thiols, and thioethers. So now we are going to do the heteroatom multiple bonds, double bonds and triple bonds. Okay? We are going to start from the easy ones, from the oxygen, because those are the ones that we have. Oxygen can make two bonds, nitrogen can make three bonds. So if we create a carbon-oxygen double bond, right? If we use that group as our base, then we have two other units on the carbon, right? Two other bonding units. When we have this group, the carbon is just been two hybridized, right? And this one is called a carbonyl group now. The carbon-oxygen double bond is a carbonyl group. Now, depending what's attached on the other two bonds, we have different family groups. So, one of the easier family group that we can think of is the situation where we have attached on the carbon, another carbon, and a hydrogen. When we have that one, this is an aldehyde. This family is the family of the aldehydes, right? Example, the aldehyde with one carbon attached to two hydrogens and the oxygen. Or if I place one of the hydrogens only, I can make this aldehyde. That's an aldehyde, right? Or if I make an aromatic aldehyde, I attached, okay, these are aldehydes. And you can think of any other possibilities. In the aldehydes, you are always going to have the carbon oxygen double bond attached to the hydrogen and something else, and another carbon, right? Now, if I replace the hydrogen with another carbon, right? If I have this, another carbon. Now this group now is a ketone. These are the ketones. So you need to have at least 3 carbons to make the first ketone. Okay? This molecule is acetone. You know, when you buy at the supermarket these nail polish removers, this is what you buy, acetone, okay? They don't necessarily have to be the same. I can have a cyclic acid, a cyclic ketone. Again, The basic thing that you are looking for the ketone is that the carbon-oxygen double bond is connected to two other carbons. Okay? So, another one, an aromatic ketone. Okay? And any other combinations. I can give you this ketone, for example. And because I put one of these groups on, it doesn't mean that I'm going to have, I cannot have another group attached to them. For example, I can have this ketone over here, and I can have a hydroxy group on the other side. I have a ketone and an alcohol at the same time, right? Now, becoming a little, changing the mode, changing one of these bonds to an oxygen. Okay, we have two possibilities. This is now is the carboxyl group. Carbonyl, hydroxyl, abbreviation carboxyl. And the molecules that have this group on are the organic acids. And if I replace the hydrogen over there with another carbon, these are the esters. And if I replace the oxygen with the nitrogen, these are the amides. Examples. I just put them together so because they are similar structure, and I want you to see the similarities and the differences. So the acids that you already know from general chemistry. Or a larger one. Okay? The basic thing that we need to see the acid is this function, the carboxyl group. So you can see it over here, you can see it over here, you can see it over here. Okay? And I can give you an aromatic acid as well. Okay? All of them have the carboxylic group, all of them are organic acids. Now, in all these organic acids that I wrote, if we take away the hydrogen and put another carbon onto it, we can make what we call an ester. So here, I'm putting on this one, okay? You can see the connection. The carbon attached on the oxygen attached on the carbon with the carbon-oxygen double bond. I make this one. Okay? Again, the connection. Carbon, oxygen, double bond. These are the esters. And if I replace the oxygen with the nitrogen, okay. Oops. Since I am in the aromatics. Okay. Or I can have, for the esters, I can also have cyclic esters. And for the amides, I can have cyclic amides. Carbon, nitrogen, okay, carbon, nitrogen, carbon, oxygen, double bond. These are the amides. The nitrogen attached on the carbon with the oxygen, that's an amide group. And I can have also the open chain amides. Any combination possible you get when you have a carbon oxygen, a carbon oxygen double bond attached with a single bond on nitrogen, you get the amide combination. Okay. Now, there are a couple of more molecules or families that I want to introduce you for the functional groups that we are going to be seeing. So I want you to be familiar with them. They are molecules which have nitrogen and oxygen, and nitrogen by itself.
Professor, I'm a little confused about the drawings up there. Which one is ester and amide?
The esters are the ones that have only oxygen. The amides are the ones that have nitrogen.
Oh, amides.
Okay? So, another family, which for the people who are into cars might become interesting. Nitro groups. Okay, we have the nitromethane. And the nitro group is essentially, the nitro group is a nitrogen, oxygen. This is the formation of the nitrous groups. We can have nitromethane. We can have the nitro group attached on a ring, like that. We can have the nitro group attached on an aromatic ring, like that, and so forth. So all the molecules that have the nitro group in the NO2, they are the nitro, or belong to the same family, the nitro family. The other interesting molecule that we have from the nitrogen are the molecules with the triple bond. Okay? These are called nitriles or cyanides. If you remember, this is the cyanide group, right? Has a triple bond. So essentially, we can have a molecule like that. We can have a molecule like that. We can have the aromatic molecule. Okay? Many of these molecules that I put on the board are molecules that we are going to be seeing soon. We are going to be studying them, talking about their chemical properties and their physical properties. That's why I wanted to get you familiar with them, get you familiar with the structure. So when we put a nitro group on the board, you know that it belongs to the nitro family. When we put a carbon nitrogen triple bond on the board, it's a nitride, it's a cyanide, and be able to recognize all these things. On Thursday, we are going to talk about their properties, how these groups are influencing, determining the properties of the molecules, and what. And from there, we are going to go on to talk about other things. But at this point, you need to be familiar. You need to be able to identify and recognize the groups. Okay, people. See you on Thursday. Please.